So taking a look at geometry. So it's asking us for linear, trigonoplanar, or tetrahedral, which is basically the same way of asking, right? Linear is SP hybridized. Tetrahedral is SP3. And then trigonoplanar is SP2. And we remember these things by the number of pi bonds or p orbitals they have. So this would be sp3 because it has no pi bonds. This carbon would be sp because it has 2. This carbon would also be sp because it has 2. sp3, 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 right? Now the things get a little different when you have a lone pair next to a pi bond, right? Because then you can do resonance. So then you choose to have a p orbital because you can put the lone pairs in that p orbital. So this nitrogen is actually sp2 hybridized because it can do so that way it can do resonance. Right? Notice how this one's sp3 though because it's not right next to a pi bond. So if you're next to a pi bond and you have a lone pair, you're going to try to be sp2 or sp so you can do resonance. So right, taking a look at two other examples. This nitrogen's already sp2 hybridized, so its lone pair is in an sp2 orbital, so it can't do resonance. Right, it already has a pi bond. Now if you look at this one right here, this nitrogen again, this lone pair is an sp2 hybrid orbital, so it's not in a p orbital, it's not in resonance. But the nitrogen is sp2 hybridized. This nitrogen is also sp2 hybridized, but its lone pair is in a p orbital because it's next to a pi bond. You get a resonance. This one lone pair is part of the aromatic system. This one's not. This one's also not part of the aromatic system. Exactly. So right. So if things are not in resonance, if they're not in part of an aromatic system, they're going to be more reactive, more basic. Exactly. All right. So how do you rank E and Z? Step 1. You cut the pi bond in half. Draw in any hydrogens. Then you look at it and say, okay, from this carbon, who's ranked higher? Carbon or carbon is a tie. But this has H, another carbon. So this side wins. H versus carbon. Carbon has a higher atomic number. So we see they're on opposite sides. So that is a E alkene. Just like with most things, people will forget the rankings. Draw on the IHs, all those kind of things. So showing a reaction here, and the question is, what effect does the amount of ethanol have on it? So first, you got to decide what kind of reaction it is. So if you look at these two things, you should be able to look at it and say, well, this is an elimination, right? I've made a pi bond. So that means you know it's a E reaction. Now the question is, do you have a reactive base or not? That's the next question. So you have a tertiary alkyl halide, so that could be E1 or E2. Either one of those works. Do you have a reactive base? You do not have a reactive base. Ethanol is not reactive, it doesn't have a charge. So this is for sure going to be an E1 reaction. What that means by saying the base isn't reactive, it isn't part of the mechanism or part of the rate determining step, that means the amount of it that you add won't matter. Because the slow step in an E1 reaction is always going to be carbocation formation. That's always going to be the slow step. So by looking at the type of reaction, elimination, tertiary alkyl halide, right? Tertiary alkyl halide, it could be E1 or E2. And then we look at the type of base, and it's not reactive, doesn't have a charge, so I know it's E1. If it's E1, just like SN1, the first step is carbocation formation, and that means it's unimolecular. That's what the 1 stands for, right? Only one species is involved in the rate determining step. So the ethanol, the solvent, the base, has nothing to do with anything. It doesn't have anything to do with the rate determining step, at least the rate. So you can add more of this, and it's not going to make it go any faster or slower. And then because the first step is carbocation formation. So an E1 reaction, you get that. There's your elim right there. All right, so pi bond reacts. It's going to go on carbon. Carbocation is going to go on carbon 1. This is the more substituted carbon. 1, 2. And so from this point, we could do a hydride shift. That's one possibility. That gives us a tertiary carbocation, which is great. Alternatively, and perhaps more likely, if I draw that original carbocation, so redraw the first one, pi bond reacts secondary carbocation to tertiary. I'm just going to redraw this here. Instead of doing a hydride shift, I also could have done an alkyl shift. 3. Now what happens there would have made this species, which of course can also do a hydride shift, and that'll get me to this carbocation, which is also a possibility. Probably not the best question for multiple choice things, but there you go. Basically, I want you to look out. What's the point? The take-home message here is, right, do you understand carbocation stability? Right? If you have a secondary, could it do rearrangements to tertiary? Yes. Could it do ring expansions? Yes. So just keeping those things in mind about carbocations, they will rearrange. That's the key. All right, epoxides. If you have an epoxide that's unsymmetrical, so you have carbon 1, carbon 2, carbon 1 is less substituted, carbon 2. In basic conditions, the nucleophile adds to the less substituted carbon. So you get this here, 1, 2. In acidic conditions, you protonate first, right? Because you have H+, you protonate, right? So basic conditions you add, acidic conditions you protonate, and you'd end up with, for that one, you'd end up with and then this would fall off to regenerate the acid. So acidic and basic conditions with ethylene oxide, you get two different regioisomers, right? Goes for different regions of the molecule. So in basic conditions you add, acidic conditions you protonate, and go for the more substituted carbon. So carbon 2. So let's say you're given something like this. The first thing you got to be able to do is recognize what's the same and what's the difference, right? So similar, I did the same exact problem for everybody way back when. I said, what's the thing that's the same, what's different? So it's easier here because there's just one thing that's changing, right? The only thing that's changing here, right, is the halogen. So we can see the difference between what's the relationship between those things. And the periodic table is based on size. Perfect. Now we've moved on. We've got a couple different things we think about, but you got to still isolate the things that are the same, things that are different. So what's the same for all of these? They're all carboxylic acids. That's not changing for any of them, right? Okay, so if we're asking which one's the most reactive acid, again, when they're ranking them, find the least and find the most, right? So then so I see that part's all the same. What parts are different here? Well, I'm seeing two things that are different. This one's not an aromatic ring, and all three of these are. I'm also seeing different substituents on these rings. So let's look at what does the aromatic ring do, right? It's gonna if the carboxylic acid is right next to the ring, it can provide resonance. If I deprotonate this, at the end of the day, we're asking if this is a minus charge, right? If that has a minus charge, that can be stabilized by resonance. Does this ring allow for resonance stabilization there? No. Right? It doesn't. Versus all these other ones will. So this is probably the least reactive acid because it has the least stable product. So I'd rank this one number 4, least reactive. Now between these three, again, I'm looking, okay, I can look at it one of two ways. I can look at it from the starting material point of view or the product point of view. Star material point of view, I'm looking for reactive bonds. Product point of view, I'm looking for stable products. This is an electron donating group. Right? It has lone pairs. It donates electrons into the ring. This is an H. It's nothing. And this is SO. This is an electron withdrawing group. Right? The sulfur doesn't have lone pairs and it's attached to oxygen, just pulling electrons from the ring. Whereas this is pushing them in. What's going to make this more delta plus? Something that pulls electrons away or something that pushes them in? Something that pulls them away. What's going to stabilize a negative charge better? Something that pulls electrons away. So this would be number 1. And actually putting electrons in makes it worse, right? So this would be the least reactive, then it'd be this one. This would be 3. And then this would be 2. Okay. 3 and 2. But again, right, it's a little more complicated, but you got to think about isolating the variables. What's the same, what's different for all of these kind of things. So I just made this one up. Again, though, for the purpose of trying to make people think about multiple factors mattering, right? So 4 types of molecules rank most acidic to least acidic. 1 is the most. Alcohol, carboxylic acid, carboxylic acid. Automatically, I know carboxylic acids are more reactive than alcohols, all things being equal. This one has this so I'm going to compare C and D to each other. So I know one of these is going to be number 1. No aromatic ring, aromatic ring. I would guess having the aromatic ring, that allows it for more resonance, right? Which is the reason why carboxylic acids are more reactive than alcohols in the first place, because they can do their products can do resonance. So I put D as number 1. So that one. And then I would say C. And now between A and B, again, what's the difference? D-protonate here, I have an O minus, but D-protonate here, O minus. This O minus can do resonance, this one can't. Resonance is always good. So it makes a more stable product, which means it has a more reactive starting material. So that's what I would go with. But again, isolating factors, thinking about these things, resonance, right? What are we asking about? Proton, deprotonation. Also be very careful about reading, right? Make sure you read it really well too. Write down your answer on a scratch paper and then go look for your answer.